award in 2006. So I can keep going, but we're very, very pleased that you are with us. And I got the pleasure to visit with him in Bangalore last year, and we were together in Netherlands for the conference that we co-organized as an ICT. So it's our pleasure to invite you here to tell us about your research. Okay, George.
Yeah, thank you, Professor Alcotti, and thank you, everybody. It's indeed very nice to be here, and I am kind of completed about a month or so, and I'll be 6 more months here, and it's very enjoyable stay here. So I am going to speak on a particular area on which I have tried to do some research on the optimum thickness design for the asphalt pavements. Now, any pavement designer would actually wish to design a pavement which is reliable. Reliable in the sense that the pavement should not fail prematurely. Pavement is, of course, will fail, but if the pavement is designed for 30 years, 40 years, it should not fail premature to before 30 years or 40 years. So it should have a level of reliability, say with 80% reliability, it should fail within the designated design period. At the same time, a pavement designer will look for something which is very cost effective, because every time you are trying to do a pavement design, you will have a number of alternative solutions. And a pavement designer will look both the things, and sometimes they are very conflicting, because a pavement designer will look for a cheap solution. At the same time, he or she wants to enjoy a most reliable pavement design which will not fail prematurely. So my talk would actually try to focus upon whether there is such a combination which may exist, that the pavement design is very cheap, at the same time it's reliable, and if so, how to design the pavement in that way. Before I proceed further, I must give at least 2 declarations. One is that this talk is about the design of pavement, means I'm not concentrating on the functional aspects or the drainage aspects. I'm only talking about the thickness design of the pavement. This is the first thing. First declaration. The second thing is that I would keep my presentation confined within whatever is the design protocol or the design system by the mechanistic empirical pavement design approaches. So which of course uses performance equations, that initial stress strain conditions are related to the longevity of the pavement. There are doubts, there are issues with that, but then I would so far this talk is concerned, I should confine myself into the mechanistic empirical pavement design framework. Pavement design involves a number of parameters, and I'm definitely not going to discuss all of these, like there are section properties, traffic characteristics, environmental parameters, and design period. All of them are considered together to design the pavements. This is generally taught in a typical pavement design class. But at the end of the day, finally, we have something called number of traffic repetitions the pavement is expected to undergo. That's one side. And the number of traffic repetitions the pavement can supply. So it's like a demand and then the supply. These two I'm trying to match. And then I'm trying to make these 2 parameters to be equal. There are various pavement design charts which are presented, which are developed by different guidelines. And once again, I'm not going to discuss these pavement design charts because they are anyway covered in a typical class of pavement design. And they would typically look like this. Of course, the NCHRP guideline, they do not use this kind of ready-made charts because they are using computer softwares to have an output as a pavement design. But this is, for example, a Shell pavement design chart, 1978. This is how a typical Asphalt Institute pavement design chart would look like. This is Austroads, 2004. This is 1999. This is our Indian design chart, 2001. They look different, but then they are conceptually, all of them are same. And once again, I'm not going to discuss them in detail because the parameters are like H1, which is the thickness of the bituminous layer. This is the H2, the thickness of the granular layer. And you can have multiple combinations. So since you have many parameters, thickness of the bituminous layer, thickness of the granular layer, then the traffic, and then the modulus of the individual layers, you may choose to plot different things with different combinations. For example, Asphalt Institute chart, it plots between the subgrade modulus versus the traffic repetitions. And that's the reason this curve looks different than the other curves. Now, I would like to take this curve as the basis, and this is a typical pavement design chart where my design parameters are the granular layer thickness and the bituminous layer thickness. And you can see that this line is a rutting curve. This is the fatigue curve. And if you take different points, for example, if you are taking point E, it is oversafe with respect to the rutting. If you are taking point F, it is safe with respect to the fatigue, but oversafe with respect to the rutting. If you are taking point G, it is both oversafe in terms of the fatigue and rutting. And if you are taking point O, it appears to be the pavement is just safe from the fatigue and rutting. That also would mean that the pavement is failing. It's going to fail simultaneously due to fatigue and rutting. So if I take this curve as the basis, then we can see that, of course, this shaded one is the oversafe portion, unshaded one is the unsafe portion, and the boundary in between these two can offer me a number of design combinations. And it's up to the designer to choose the best possible combination. Of course, the answer is going to come from the economy, because out of this combination, what would be interested to check that which one turns out to be the most economical. So we can think it in this way, that if we just look at the bituminous layer thickness and the granular layer thickness, and if we suggest that there is this kind of a formula which may exist, that the total cost of a pavement is equal to fixed cost plus the unit cost of H1. H1 is the thickness of the bituminous layer, plus the unit cost per unit thickness into the thickness of the granular layer, which you may say that this is also arguable because the cost is not actually linearly proportional. But then so far, let's assume that this holds. And if this holds, then you can see that between H1 and H2, it's going to represent an equation of a line. And therefore, I can think of a line, or I can think of another line. I can think of another line. This anybody can plot who is not a pavement designer, but just from cost consideration, these parallel contour lines can be drawn. And the TC triple dash would indicate that this has a higher value than the TC double dash, and so on. Now, it's interesting. It would be interesting if we can superimpose the cost contour lines with our original structural pavement design lines, and there could be multiple possibilities. Now, one possibility is that the cheapest cost comes there, or the other one could be the cheapest is this, and then there could be the cheapest can turn out to be the intersection of the fatigue and the rutting curve, or somewhere here. So we did some kind of exercise, and we have seen most of the cases for all practical values of the thickness of the bituminous layer and the granular layer, the cheapest option turns out to be the point O, which is the intersection of the fatigue and rutting curve. So therefore, my design solution appears that the intersection of the fatigue and rutting curve would give me a solution where the pavement is going to fail simultaneously due to fatigue and rutting. That's a question, again, I'm going to ask, that whether this is good to have a pavement failing simultaneously due to fatigue and rutting. And at the same time, this point gives me an option where the cost is the cheapest one. Now, let's proceed further, because all of us know that this is a deterministic design principle I talked about. And we know that there are variability, extreme range of variability which exists in a pavement design. And therefore, it would be a good idea to check their variability. And there is a standard concept of evaluating the reliability of the pavement design. And in fact, these are the studies I took from the old papers which was published by Professor Mike Daughter. So I have been following his papers extensively to do this part of the study, where we consider the variability of all these parameters. So therefore, you can see that the variation of the traffic volume, axle load, and all that. Design period, of course, does not vary. And then we get the variation of the expected traffic, and similar way, variation of the material properties, layer thicknesses, and loading configuration, coefficient of the performance equation, and finally we get, once again, the story of the demand and the supply. So this is the expected traffic, this is the demand, and this is the supply the pavement is going to offer. And then these two together determines what is called reliability. Once again, I'm not going to discuss how the reliability is estimated for a typical pavement, but then quickly, This is how a typical fatigue or rutting distribution we have found. It follows a log normal distribution for any given pavement. So we can see if there is a distribution like this, allowable traffic is much lower than the expected traffic. That means the traffic always exceeded the number of repetitions the pavement can sustain. In that case, the reliability is 0%. Or if it's otherwise, that the expected traffic is much less always than the allowable traffic, then the pavement is 100% reliable. Now, of course, in all practical terms, we are not going to have a 0% reliability case or a 100% reliability case either. We are going to have something in between, and that's how the reliability is defined. These are standard definitions. This is called safety margin, T minus N, then the reliability is defined like this. And there could be another definition. This is damage factor T divided by N, and the reliability could be like this. If you do derivations, you can actually show, you can mathematically prove that no matter what the distribution of T and N are assuming, they will actually turn out, you can actually find out the same value of the reliability in both the cases. So therefore, my point now is that instead of doing the deterministic design, it would be a good idea to check the reliability of the pavement, because I come back to the same question that whether it's a good idea to have a pavement which is going to fail due to fatigue and rutting simultaneously. So you can actually develop a reliability charts. So that means it's obvious, because as more and more thickness you are providing, the reliability is improving. So you can have for a fixed values of the H2, you can have different curves. And then for different failure modes, the curve will look like, as the thickness is increasing, H1 is increasing, reliability is increasing. This curve looks different than the earlier curves I have shown. If we go back to the earlier way of representing the curve, that was the deterministic design, and you can see the red lines that says that the reliability, if you are choosing a design from a point from the red marked line, then the reliability is going to be higher than if you would have chosen this line. So therefore, this is how the reliability concept is taken in the pavement design. Now I have two questions, that estimation of the reliability of a given pavement, which is easy because you can consider the variability of all the parameters and you can finally simulate. Of course, it amounts to a large number of simulation runs, and typically it is done by Monte Carlo simulation technique. That's because we cannot actually analytically find out the reliability of a typical pavement. That's because the difficulty in the analysis, we cannot actually find out that how much is the how the distribution is going to look like when the distribution of the other input parameters are known. That does not work well for a pavement structure, given that the analysis of the pavement is very complex, where elastic modulus and the thickness and the tire pressure are the input, and you are getting the number of repetitions it can sustain as output as a distribution. So most of the time we end up doing a kind of simulation run where we estimate the reliability of a given pavement. But the second part of the question is more difficult, because you are going to design a pavement for a given reliability. And design, as any other design case, is going to be an iterative process, because I think the next slide would explain it. This is the expected traffic, and this is the repetitions the pavement can sustain. And in this case, it's not a single line as we discussed deterministically. It's going to assume a distribution. And therefore, you have to actually keep moving this one, because this is fixed. This is kind of fixed, because this is what the traffic engineers are providing me, that this is the distribution of the traffic the pavement is going to sustain. And this is the number of repetitions the pavement can sustain. And as a designer, I have the choice to change the thicknesses. And finally, because when this distribution was there, that was too safe, because the expected traffic never was equal to the number of traffic the pavement can sustain. So therefore, you consider reducing the thickness bit until this intersects, and the negative portion is the portion which says that it goes out of the limit, and therefore you can design a pavement depending on what reliability level, 80%, 60%, 20% you want. So now, if you now superimpose, remember we have talked about the intersection of fatigue and rutting curve, we have talked about the cost, and it's interesting that we can now superimpose the concept of the reliability on this curve again. And if we do so, we'll again see this is a particular reliability, this is another reliability, this is another reliability level. And if we do so, we can automatically see that the intersection of the fatigue and rutting curve also shows that, for example, as I have shown in the last chart, that as you are going up, your reliability value is increasing. This is true for the fatigue and rutting. And the intersection is also the cheapest cost line. So therefore, you are in a position that you have to satisfy a particular value of the reliability for the rutting. You have to satisfy a particular value of the reliability of the fatigue. And at the same time, you have to look for an option which gives you the cheapest cost, is also the intersection point. And therefore, it seems to be a feasible solution. And now, in the search space of the thickness H1 and H2, which is the bituminous and the granular layer, you have to be in a position to quickly find out these optimal points. And once again, nobody is going to do a large number of calculation check to find out where exactly the point is located, because in a practical value of the H1 and H2, which may say H1, for instance, the bituminous layer thickness may, for instance, may vary between 50 millimeter to 500 millimeter. The thickness of the granular layer may also vary between 50 millimeter to 500 millimeter. So it becomes a very cumbersome operation that you have to keep looking for all the points, and you have to do a simulation considering the variability of all the points, and then find out reliability, and then you are not happy with the reliability value because you wanted to achieve a different reliability, and switch to the next point and keep doing it. So this would be a good idea to employ some kind of an optimization technique where the optimization function can be simply defined as this, that the reliability of the fatigue, which is a function of the H1 and H2, minus the reliability of the design fatigue, which I wanted to achieve, the mod of that. This is the simplest way. Of course, one can again argue that this is not a objective function. We should, because sometimes using mod makes it discontinuous in terms of it jumps. So you can do a square and add and all kinds of objective functions you can choose. And then we have adopted a simple simplex optimization principle where you form a triangle search, and then you keep moving this triangle, and finally you are in a position to reach to the optimal point very quickly. And it can show that out of a range of, this is the range of the granular layer, this is the range of the bituminous layer, you can see in the 8th iteration we were able to reach to our optimal design point. Now, this principle can be extended to design of 3-layer cases, because 3-layer means 3 design layers. So that means I have H1, H2, H3. It is quite possible, because you may not have a single bituminous layer. You may have different bituminous layer. You may have different granular layers as bases and subbase, and you would like to optimize all of them together to achieve your reliability. So when you have 3 variables, it turns out to be in a 3-dimensional, because you need to have H1 and H2. And instead of getting a point, in this case, you will get a line, obviously. And therefore, your OF equal to 0 line, which is the objective function, that is the all reliability limits are individually satisfied, will lie on this line. And therefore, you have to again invoke some kind of a search operation where it will be able to find out the least cost one, because you want to satisfy both the reliability as well as you want to achieve the least cost option. So this is how it can be done. I'm not going to discuss them because we worked on it, and somehow we could get the results with whatever simple algorithms we have used. So for different values of H3, we are able to find out a cost optimal point. So that means if I have 3 variables as H1, H2, H3, it is possible to find out, satisfy the individual reliability requirement for the fatigue and the rutting, and it is possible to get the optimal design point. So also possible if we have 4 design variables, and so also possible if we have a number of design variables. So this is a numerical part of the story, and one can employ a suitable optimization scheme, even better than the one which we have used to quickly reach to the optimal value. But then I would like to zoom the story out further, because if you have noticed, I have only discussed about the fatigue and rutting, and that's not all about the pavement failures. At least if you refer to the NCHRP documents, it will say at least there are 5 such failures, and therefore I need to expand the scope of my approach to the different other failures: fatigue, rutting, low temperature shrinkage, thermal fatigue, and top-down cracking. Now, I can, of course, it's very easy to write down these as the optimization problem, that I want to minimize the cost subject to the reliability of the individual distress parameters I am considering now. All of them may or may not be the function of the thickness, and they should at least be greater than equal to the specified design reliability level. So in 3 lines, the entire thing can be translated, the entire pavement design problem can be translated as an optimization scheme. But again, it's not, of course, very easy, because then the dimension of the problem has increased many folds, and then it's not very easy to solve it. But then I would like to touch upon a little differently than simply saying that we have to employ an optimization to solve it. I'd like to look the problem in this way, that whether all these 5 distresses, are they connected parallelly or they are connected in series from the reliability point of view. Let me explain this. The parallel and series connection means that think of a bicycle or a cycle with multiple wheels is being operated by a family member. So the husband, wife, and the children, they all are kind of pedaling and the cycle is moving. Now the small kid, if he or she is not pedaling, then that does not harm, the cycle will keep going. So this is like a this kind of a connection of the reliability, because one of them, the pavement has failed, then the pavement is still surviving. The series one is, think of an axle, whereas something breaks at the axle, then no matter how many operations the axle is associated with, because there is a breakage in the axle somewhere, it just refuses to move, refuses to rotate, and therefore the whole machine does not work. So reliability comes down to the 0, breakage of a single part. Or think of a coupling arrangement where I have multiple bolts. If one of the bolts is not working, that's fine. Still the coupling can rotate. So that is a concept which is again a very, very standard concept used in the reliability, that whether the distresses are connected in series or connected in parallel. If they're connected in series, that would mean that if anything is, if the pavement has failed due to this, one of them, then the pavement refuses to survive. Now it is we who have to now see that whether the pavement failure, we could actually think in terms of whether they are connected in series or they are connected in parallelly, and this is we have to do some initiate some thought process on that. Of course, the reliability is reliability in this case would be defined by this. Reliability in this case would be defined by this. This is once again standard concepts used in reliability. This is union, this is intersection, because you see reliability is 1 minus the failure probability. So the failure probability intersection means the probability that all of them fell together. And here the probability of at least one of them are failing. So that's how you can, of course there could be 2, there could be 3, they may fail, but at least one of them is failing, is failure, and 1 minus that failure probability gives the reliability. So since I have 5 variables now, I have to really look for that how they are connected. Now I would like to take this discussion little further, thinking that I wanted to check that whether they are really related to the thickness or not, because you remember in the beginning of my presentation I started the discussion that I am going to concentrate only on the thickness design aspect. Now I have to see whether these 5 distresses, whether they are or not related to the thickness. If they are not related to the thickness, then they would be used not in the structural thickness design, which I'm discussing in this presentation, but will be used elsewhere. Now, of course, load fatigue is related to the thickness, as well as is also related to the mixed composition. Thermal fatigue. Now, all these tick and then the cross I'm making are not kind of the final statement I'm going to make. And this is just an approach. This is just a logical framework I'm trying to present here. It's not the if you argue strongly that thermal fatigue is indeed related to thickness, I'm going to agree with you, because it's just how I'm arranging this thing in the pavement design is what I'm going to say here. So rutting is related. So also the thermal shrinkage is probably not known whether they are related to the thickness. Then the top-down cracking, whether they are related to the thickness, is possibly not known. And of course, I can expand these issues further, arguing for and against whether they are or they are not related to the thickness, but I am skipping the entire presentation. For example, just if you look into the NCHRP guideline, it will say that the thermal fatigue is related to the no, this is top-down. Top-down is related to the thickness, and then this kind of a graph is presented. You can see that there are more amount of top-down if the thickness is smaller. If the thickness is larger, then the top-down cracking is not so prevalent as this case. So these are yet to be established or confirmed that whether they are related to thickness or not. But I will follow this kind of an approach so far, that fatigue and rutting, they are at least related to the thickness, and others we do not know for sure. And if it is so, then I can actually have the privilege of dividing the pavement design into 3 phases. The first part is that thermal fatigue consideration, which I want to say that they are not probably related to the thickness. Of course, they are related. You can argue, because you see, if the thickness is more than the stress values, there would be a thermal gradient, and the stress values could be more, and the variation of the stress, there could be for a larger thickness, there could be a larger variation of the thermal stresses that may lead to a larger possibility of the thermal fatigue. But so far, let's assume that thermal fatigue is not related to the thickness, and if so, then the thermal fatigue would rather be a mixed design parameter than considering it something which is affecting the thickness. So therefore, I could place this as a phase 1 of my pavement design, where I am only taking a decision based on the mixed design, and then I come to the phase 2, where I have to think of the load fatigue as well as the rutting, which obviously are related to the thickness. And the third phase is the top-down cracking and the thermal shrinkage considerations, where they are probably or may not be so strongly related to the thickness. So therefore, the design approach becomes this, that first you are ready with your mix and check whether that mix is good enough to sustain the thermal fatigue or not. Then we are using that mix for design of the pavement from the fatigue and rutting considerations. They are obviously related to the thickness. And in the third phase, where the top-down cracking and thermal shrinkage may or may not be, even if they are related. For example, we did some study on thermal fatigue. We found that they are related to the thickness, but not very strongly. So if you agree that top-down cracking and thermal shrinkage considerations are related to some extent to the thickness, but not very strongly, then place them as a phase 3 of the design, where you are looking at the mix side, as well as you are looking, checking whether thickness provided primarily due to the fatigue and rutting are safe enough to consider the top-down cracking and the thermal shrinkage. It's like typically like we do a beam design in our cement concrete design, that we design the beam, the thickness of the beam, the depth of the beam from the bending moment considerations. Additionally, we do a check for the shear and the serviceability in terms of the deflection. So this is a design approach which is suggested. And if so, therefore, as I have shown you in the previous slide, or the slide previous to that, is that the question is whether all these 5 distress parameters, distress modes, they are connected in series and parallel. And now I place the argument that if they are not dependent on the thickness, therefore I can keep them aside and I can do a phase 1 and phase 3 of a check. But then in phase 2, we have to just think once again the fatigue and rutting as we did earlier. Of course, the issue remains of the integration of the mix issues and the structural thickness issue, and sometimes they are conflicting. For example, you need to have a very high stiffness, because if you have high stiffness, then your stress and strain values will be low. But high stiffness bituminous mix is not always very good, because they tend to become brittle, and therefore their fatigue properties fall. And there are always the conflicting criteria. Therefore, this suggestion or the idea is that let's not keep the mix design issues as a separate entity, that a mix designer designs the mix and then gives a pavement designer to design the pavement. There is a need that the mix design and the structural design issues are actually thought combiningly. So there are issues like a stiffer asphalt mix or a softer asphalt mix, or more air void, because more air void and low air void issues, etc. So I come back to the phase 2 of my design as the load fatigue and the rutting consideration. Now once again, I have to look for 2 possible definitions of the failure, as I have shown you, the parallel and the series connection. Overall reliability due to fatigue and rutting, whether I would define the failure due to both fatigue and rutting, or the failure due to, at least due to fatigue and rutting. It's like the pavement, it's like an analogy can be drawn, like the kidney fails and the heart fails, whether this is a better option than either one of them fails. Okay, so this of course we have to come up with a suitable definition that which one works good. I would like, personally, you may again disagree, that I would like that this definition is all right. Failure either at least due to fatigue and rutting. And if this is so, a simple probabilistic calculation will say that the fatigue probability and the fatigue reliability and the rutting reliability, if you multiply, would give the reliability value. So again, once again, I go back to the chart which I was showing, the bituminous layer thickness and the granular layer thickness. So then if you are plotting the reliability values, they would look like this. So this is as you go up, 0.4, 0.5, and 0.6 like this. This is about the fatigue part. And similarly, the rutting part is like this. And we just now agreed that we are going to use at least either due to fatigue and rutting is our definition of the overall reliability. And therefore, I can multiply the values and keep writing here. And then these are my overall reliability values. And then I can actually, because the graph looks clumsy, I can actually remove these, and I am left with these points. And then I can actually draw overall reliability contour on these. And this is a 0.2 line. This is a 0.3 line. So remove the points also, so that the graph should not look clumsy. So this is my overall reliability in terms of the fatigue and rutting, with the definition that the pavement failure is defined when the pavement fails either due to fatigue and rutting. And remember, I invoke the equi-cost lines once again, and then this turns out to be my good design, because this is where I have the this is the equi-reliability line, this is the equi-cost line, and this is the point where I can enjoy the maximum reliability for the whatever cost. So it's like, for a given cost, I have to achieve maximum reliability, or for a given reliability, I have to minimize the cost. So this chart is trying to throw some light that this is possible, and we can do a numerical optimization to reach at this point where I can satisfy the reliability level subject to the minimum cost, or for a given cost, I can achieve the maximum reliability level. I would further, how much time I have? 5-10 minutes, okay. So I would like to further zoom out the story. See, all what I have so far talked, of course, I discussed about at least 5 structural distresses that can be brought into the pavement design, but all what I have talked is actually the pavement design for the first time. But then this is not about the pavement design, and one has to really consider the overlay design or the pavement the thickness requirement at the subsequent stages, and everybody talks about life cycle cost optimization. So we have to actually go to the life cycle cost issues to find out how the cost, the overall cost can be minimized in terms of maximizing the reliability values. Now, once again, this is a little bit of a classroom material, and I'm going to skip this just quickly. If this is my granular layer thickness, this is my bituminous layer thickness for the traffic A, and that is the bituminous layer and granular layer thickness for the traffic B. So after the expiry of the traffic B, I am not going to actually put the thickness, which is the difference between these two, shown as HB minus HA. That's simply because there is some part of the bituminous layer which has already deteriorated and which is contributing to the granular layer. And of course, there are different approaches, and it can be kind of conceptually shown that they mean basically the same. So if I come back to this graph, I would maybe little quickly I will show that if the design should be done this way, that this is my INI for the traffic level A, this is my granular thickness, this is my bituminous thickness. Now, after the expiry of the traffic level A, if I assume that the bituminous layer thickness has completely deteriorated and converted to become a granular thickness, so therefore I have to make use of this as the granular layer thickness, and subsequently be in a position to find out the thickness required for the additional thickness required for the remaining amount of traffic B minus A. Now, this is already known, this is kind of established, but why I pose this issue is that if you decide in any typical maintenance optimization papers or overlay, because there you have problems like when you are going to, what should be your times of the individual overlay and how much overlay should you put. In all such papers, it is generally assumed that 100 millimeter of overlay in each cycle means the same, which basically is not. Because the 100 millimeter overlay I'm putting in this cycle, this 100 millimeter of overlay will deteriorate and probably would convert to some form of equivalent granular layer, or maybe better than that. So next time I'm deciding to put a 100 millimeter overlay, I'm actually providing lambda into 100 millimeter of overlay, because I'm getting some additional thickness as my benefit. So that's how we worked on Optimum maintenance cycle, and this is a paper which is under review in this TRB now. And then there are a series of papers published by Professor Madanath Lee and Madanath and all that. So what we did, we actually separated the functional and then the structural aspects, And then we also considered this factor lambda, which considers that the benefit, additional benefit I'm getting in the subsequent equal amount of overlay. And this part, this integration part is the cost due to vehicle. This is a standard approach. This is the vehicle operating cost. This is the cost due to overlay. And I'm summing it up for the entire analysis period. And I'm trying to minimize to find out the optimum number of overlay cycles I should provide, so that the total cost over the entire design period turns out to be the cheaper. So therefore, that's again the deterministic part. But ideally, we should do, if we are interested to carry on with the reliability-based approaches, we should do this way, that there is a reliability value, which is good. The reliability value will subsequently fall, and then once it reaches a terminal value, then I provide an overlay. So that means the overlay is decided from the overall reliability consideration, because in that way you are able to combine the structural issues, functional issues, and then you are able to consider many distresses together when you are considering in terms of the reliability. And fortunately, or maybe unfortunately on my part, because somebody else has done this part of the research. So it would look like this, that this is my expected traffic, and this is the pavement repetitions that the pavement can sustain. Now, I am providing additional overlay, and then therefore the number of repetitions the pavement can sustain, I'm enhancing that. But then traffic is again gradually approaching and catching it up until the reliability becomes, the negative portion, as I told, is not good, because that's where the traffic is exceeding the number of repetitions the pavement can sustain. So it reaches here, and then once it reaches a cutoff value, we recommend that there should be overlay. As I said, that this group has already published at least 1 or 2 papers in this, but of course I think this is the area in which I wish to go forward with more research, because there are some issues in my mind which can be taken care, which this paper has not done so far. So that's kind of the end of my presentation. I would like to thank the Fulbright Scholar Program, and then these 2 organizations, United States India Educational Foundation, which took care of the Indian part of it. Now the Council of International Exchange of Scholars is handling my stay here. So I thank Fulbright for the sponsorship of my entire stay here. And of course, my students, those who have contributed, with whom I disagreed and argued, and then they have showed, no, actually this is this. So I thank, because I presented a number of my earlier works with my different students to develop this idea. And thank you very much for your patient hearing. This is a picture of my campus, and it's raining now. Of course, this picture I took 1 year back, but then this is how it looks. Thank you very much for your patient hearing.
I've never seen an empty street like this in India. Questions? I have a question, I guess. If you go back to the one about the maintenance, yeah, that would do it. The one after this, yeah. Now, in this model here, are you assuming here that the time for the overlay is constant, or the traffic is constant, or yeah, what is?
That's once again a modification over the Balanar's paper. He has assumed that traffic and year is constant, which is not correct, because if I am taking as a scale of the year, my traffic is different. So we did the optimization in a traffic scale, and then converted into year scale. So my year is gradually shrinking. Year in terms of the subsequent overlay is gradually shrinking.
And you are going with each overlay, you are getting back to that structural capacity every time?
Yes, what we did some random trials, and we found out a factor of lambda, that addition of 100 millimeter would enhance how much of the extra life. So I multiplied with that factor. Yeah, but then we did an analysis, because but using the same performance equations to find out the strength.
You are getting to the same structural
Yes,
capacity,
yes,
that's what I'm saying.
Yes.
But the time for getting to that structural capacity is lower each time
Yes.
for an overlay?
Yes,
Each
yes,
less?
yes, yes.
Okay.
Yeah. So that is the modification we have suggested. Because the original formulation is not ours. There are 2 or 3 papers by Professor Madanath.
Yeah, I read some of his
Yeah,
work. That's
yeah,
where I had a
yeah.
little problem. That's why I want to see
Yeah,
what you
so
did.
I guess our paper has able to, we have raised 3 points and we could, but what we could not do, his expression was a closed form expression because it's a geometric series and he could actually sum it up to infinity and he could develop an expression where it was like a closed form expression, whereas in our case it is not so. So it is from 1 to p, p is number of cycles. So I can take p as very large.
And when P is ended?
When?
Because P is your number of overlays?
Yes.
What is the maximum number you get?
I think in our example, in 150 million standard axles, we had 5 overlays.
Okay.
But then this is just an example. So,
Yeah. Questions?
My related question would be, for the J+1 cycle, is it physically possible to go to the same structural capacity? Like after 4 overlays, can we ever go back to the same structural capacity? Like, I mean, the top straight line, should it not actually be bending down?
These are,
Of course,
yeah, these are,
that's why
somebody has to, yeah.
It's one of the
Yeah.
assumptions,
So our assumption is that if the time gap between the 2 consecutive overlay is coming to be very short, then we should actually recommend for a reconstruction rather than overlay. Yeah. But then at the beginning of my presentation, I said that I am going to go with the typical performance or the transfer functions, which itself is very arguable actually. So based on that, this is developed. And once you don't agree, then therefore things don't work.
Other questions?
Come on, guys.
The model that you have for the pavement, is that considered the same model for the different failure that you consider in the phases? Is that regardless of the capacity of your pavement, the structural capacity of the pavement? So do you have different failure criteria for different pavement capacity?
Are you asking about?
Like what's dictating the failure criteria for the pavement? If you are dealing, let's say, with a heavy traffic pavement or a low traffic pavement.
No, there is
are
nothing.
you considering? No,
There is nothing as such because I am saying that I am picking up any performance equation. Now one can of course upgrade it to different performance equation for different types of pavements, different traffic conditions, and also, for example, rutting, I am using the subgrade, the vertical strain on the subgrade, and one may disagree and say that the strains at other levels and other positions also have to be considered. But then my presentation was more of a conceptual framework, and one can always have add-on to make it better and more rational.
Right.
Yeah.
If there is no other questions, thank you so much.
Okay,
We
thank
truly
you.
appreciate it.